So on page 89, we're asked to derive series for Maclaurin for sine and cosine. You may be thinking to yourself, oh, we might have already done this. I feel like we've done most of this. And instead of beating this concept to death, I figured why not just take our work and bring it back in. So from page 84, we have the work that gave us the 5th degree polynomial. And from page 87, we had the 8th degree polynomial. We really just need to determine a pattern that emerges here. All right, so let's focus on the sine first, obviously. So looking at this, I see a coefficient of 1 in all cases, so that's great news, an exponent of 1, and a denominator that appears to be odd as a factorial. All right, so if that's the case, and I want to determine p sub n of x, I'd be looking at, so all this stuff, but then the generalization is going to have to incorporate a couple of different things. One, I'm going to have alternating series. All right, so, and that's good news because that's going to involve the alternating series test when it comes to determining under what circumstances it'll converge. All right, so I have odd numbers. Well, how do you get an odd number? Well, an odd number is 1 unit away from an even number. So if I'm starting at 0 and I want to end up with a 1, one way to do that would be to say 2n, 2 times a 0 plus 1. Right. If I plug in a 1, I get a 3. If I plug in a 2, I get a 5, and so on. All right. Now my signs start off with a positive, so it's going to be -1 to a power. It's just a question of what that power is going to be. Do I want that power to be odd or even? So if the power is odd, it would be negative. If the power is even, it would be positive. If I want this to start off with n equals 0, then I would make this a power of n to guarantee that my first exponent is even, which would in turn make the -1 a positive number. The x values are the same as the odd numbers and the factorials in the denominator, so I'm going to say x to the 2n plus 1. All right, so this would be my general term, and so all I'd have to say is the sum from n equals 0 to infinity of that, and that would represent the sine function. Okay, so if we want to use the alternating series test, we have to show that the series that we're using is decreasing in all cases. So I just took the liberty of jotting this down as a little bit of a time saver. All right, so if we do that, we pull out the a sub n. We could make the assumption that a sub n is decreasing. The issue that we run into with that is the presence of the x. All right, so dependent on x. So without knowing what role the x value would have in this whole thing, we could run into a little bit of trouble. So we'd have to make an assumption on what the value of x is. So if x is 0, we're fine because the top would be 0 and the bottom would outpace the top and it would be okay. If x is 1, the top would be 1, the bottom would outpace the top, and that would be okay. But if x is 2, what would happen? All right, so we'd have to start thinking about, all right, under what circumstances would this actually allow us to have a decreasing series? All right, and then from there, we'd have to get into the actual test, which is finding the limit as n approaches infinity the issue that we have here is that we would not be able to separate the x and the x and the n. We could pull part of the x out. We can make the x to the 2n plus 1 into x to the 2n times x to the first and pull the x to the first out, but we'd still be stuck with the x to the 2nth power. All right, so it'd still be reliant on the value of x. So depending on what x is, which we don't know going into the problem, we'd be in a pickle. All right, so what we'll try here is the ratio test. All right, so we can do this with the -1 included or excluded. You'll see it's actually not going to make a difference. So I'll show you. So the limit as n approaches infinity of all of these n values increased by 1, all right? So just kind of off on the side here, I'll just do 2. Instead of n, it'd be n plus 1, distribute. 2n plus 2 plus 1 is 2n plus 3. All right, so we're going to have -1 to the n plus 1 times x to the 2n plus 3 over 2n plus 3 factorial over -1 to the nth x to the 2n plus 1 over 2n plus 1 factorial. All right. So it's definitely a mess, but it's a manageable mess. All right. So just focus on the negative ones for a sec. Limit as n approaches infinity. That -1 to the n plus 1 could be thought of as -1 to the nth times -1 to the first. All right, now I'm just going to kind of gloss over everything else for a sec here. We have a -1 to the nth on the bottom. That's going to cancel. So we're just going to be left with a negative first. All right, a -1 power. So that's good news. All right, now as far as the x to the 2n plus 3, I'm going to write that as x to the 2n times x to the third. On the bottom, so focusing on this guy, I'm going to write it as x to the 2n times x. So gone, gone. Then for the factorial, 2n plus 1 factorial, I really can't do anything with that. But what I can do is think about what I'd have to multiply 2n plus 1 factorial by in order to get 2n plus 3 factorial. So I'd have to multiply it by 2n plus 3 and a 2n plus 2, decreasing by 1 every step of the way, times the 2n plus 1 factorial. So then the factorial part is gone. And now, yeah, it's still not pretty, but I've now released the x from captivity. I can pull the whole thing out. All right, so this x will go into this one, x squared times. I'm going to highlight. I have a -1 and an x squared that does not need to be in the limit anymore because they don't have n's in them. So -x squared times the limit as n approaches infinity of, well, this is gone too. Well, it's just a 1 on top now. 2n plus 3. 2n plus 2. The bottom will outpace the top, so it'll go to a 0, which is great news, because this is going to converge by the ratio test, because this whole thing needed to be less than 1. All right, so this is going to 0. 0 is less than 1. for all x. So that's on negative infinity to infinity. All right, so it seemed like alternating series. In fact, it was kind of like a combination between alternating series and the ratio test. So AST inconclusive, by ratio test converges. All right, now for the cosine function, well, I guess I should probably put in what the relation is, right? Into the little box here. It's going to be x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th plus on and on and on, all the way up to the nth term. And then that'll, if I can get some room here, that'll give us this big mamma jamma here. There we go. And so now we have our second of the Maclaurin series. All right, so same idea for the next one. A general rule, now we're dealing with even numbers. So going from n equals 0 to infinity, we would be looking at just the same general idea. All right, so we're starting off with a 0 factorial. All right, so 1 over 0 factorial x to the 0th. Then negative 1 over 2 factorial x to the 2nd. So these are powers of 2, but they're also multiples of 2 for n. All right, so we have alternating starting with a positive. So n factorial wouldn't get the job done. I need a 2n factorial to make it even. And then it would be x to the 2n. All right. So that gives us this relationship, which, cutting right to the chase here, gives us, if I can get it to fit, I'm gonna have to shrinky dinky it down. It's gonna give us all this, including the general term. So plus dot 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 plus, I'll have an equal sign over here. And now, for the sake of brevity, and also for the sake of not being overly redundant, we can assume that if something is everywhere defined for sine, it's probably going to be that way for cosine. But I can also tell you that using a similar technique to what we just did, you can determine the convergence using the ratio test for the cosine function as well. All right. So I'll let you do that on your own.